Welcome to this session. So, in this session we are going to discuss about wave propagation. So, what are different phenomena which are related to the wave and how the wave will be propagated, what are the equations and how the wave will be characterized with these equations, and what are different characteristics or features when the wave is traveling in different medium, we will discuss in this session. So, exclusively this is for electromagnetic wave, that the wave contains of electric field and magnetic field. So, here what we do is we will go step by step procedure as how to derive the equations. So, before that let me describe what are the features of a medium. So, because the medium is very important for the wave propagation, we are supposed to understand what is a medium or what is the channel, and in that the wave is propagating. Here how to describe the medium. So, medium is nothing but simply the place or the space between the source and receiver. So, let us take a communication system which consists of some antennas. So, if you take two antennas, let us take this is the transmitting antenna and let us take this is the receiving antenna. So, here what we have is a communication system which consists of two antennas, a transmitting antenna, receiving antenna. The place which occupies between these two, that is from this point to this point, will be treated as our channel or medium. That here in most of the cases, in present days, in most of the cases this medium is free space, but in many cases that may not be free space always, but sometimes we have to consider a dielectric medium. The dielectric may be a pure dielectric, that is a lossless dielectric, or a lossy dielectric, or sometimes we may consider a conducting medium. Sometimes we have to consider a free space as the medium. So, for that what we have to do is we have to observe how the wave will propagate in all these mediums and how the characteristics of the wave will vary in according with that particular medium, and we have to interpret that particular phenomena. So, now what we have to do is just we have to observe what are different mediums we have. As we discussed, free space is the most wide medium what we are observing. So, how the free space will be characterized? Remember, every medium will be characterized with three parameters. They are the conductivity, permittivity and permeability. So, based on these three parameters, we can characterize the medium. That if the conductivity is something, if it is very high, then it is said to be the conductor. Like that, what we have to do is we have to describe the features of a medium. So, briefly I will give you what is characteristic of a medium. So, let us take the first medium as dielectric. So, for the dielectric medium, once again this will be categorized as two, a lossy dielectric and lossless dielectric medium. For a lossy dielectric medium, that sigma is not equals to 0. So, if you are taking a pure dielectric, obviously there will be no conductivity to it, but here what we are considering is a lossy dielectric. For lossy dielectric, some conductivity will be there. So, sigma is not equals to 0 and the remaining all are same, that the permittivity epsilon is equals to epsilon naught epsilon r and permeability mu is equals to mu naught mu r. So, simply whenever we are observing a medium which is a lossy dielectric medium, just we are supposed to take these quantities, and for the same dielectric if it is lossless, as we are saying it is a lossless, obviously the conductivity must be equals to 0, that sigma is equals to 0 and the remaining quantities are same, that epsilon is equals to epsilon naught epsilon r and mu is equals to mu naught mu r. Then it is said to be simply lossless dielectric medium. This is a medium, it's a widely which is useful for us. And the second type of medium is conductor. For conductor, as we know, the conductivity is very high. So, what we do is we will take a very high value for the conductivity, approximately infinite. That is, sigma is approximately equals to infinite. That what we consider. And epsilon must be equals to epsilon naught. That is, the permittivity is equals to permittivity of the free space. It will have some other permeability. Then the permeability is equals to mu naught mu r. So, whenever we are considering conductor as a medium, then we are supposed to take these conditions. So, what we do is we will derive the general equations or general characteristics we will observe, and in that one we will substitute these quantities to modify the equations or characteristics. And the third type of medium is a widely used and very important medium, that is free space. For free space medium, so as we know, free space has 0 conductivity, so directly we can take sigma is equals to 0. that the conductivity is always equals to 0 for the free space, and epsilon is equals to epsilon naught. Since the relative dielectric constant is 1, epsilon is equals to epsilon naught, and mu is equals to mu naught. Relative permeability is equals to 1, therefore mu is equals to mu naught. So whenever we have free space as a medium, we are supposed to apply these conditions. So this is a brief introduction about the medium what we have. So what we have to do is we have to go for the wave equations or the characteristics of the wave, and how the phenomena of the wave will vary, or all this will be changed in according with the medium will be observed by substituting these particular parameters in the quantities what we have. So what we do is we will consider the most generalized medium. The most generalized medium is the lossy dielectric medium. It is a lossy dielectric medium. We will have sigma, epsilon is equals to epsilon naught r, mu is equals to mu naught mu r. All the quantities are existing and they are generalized. Therefore, what we do is we will consider a lossy dielectric medium as the most generalized medium, and we will try to derive the equations for waves in that particular lossy dielectric medium. So what we do is we will start our discussion with the lossy dielectric medium, then we will go for remaining mediums later. For a lossy dielectric medium, as we observed, sigma is not equals to 0, epsilon is equals to epsilon naught, mu is equals to mu naught, keep it aside. Apart from that, to derive the wave equations, we require some base. Here already we learned time varying Maxwell's equations, the Maxwell's equations in time varying fields. They are very important for observation of any wave propagation or wave phenomena. That what we have to do is just we have to take those Maxwell's equations which are meant for time varying fields, and we have to modify those equations in according with the conditions what we have. Then what we get is a pure wave equation for electric field, a pure wave equation for magnetic field. A step-by-step procedure. It's a very simple procedure that what we observe now. So before that, just what we have to do is we have to recollect the Maxwell's equations in phasor domain. That take the time varying equations in phasor domain, write them. What is the first equation? The first Maxwell's equation is del dot D is equals to rho V. That is the equation what we are considering initially. But before that, let us assume the medium what we are considering is a homogeneous medium. So what do you mean by homogeneity? That everywhere, so wherever we are considering the characteristics of a particular medium, they will not be altered. That if you are considering epsilon, that epsilon is constant throughout the medium. If you are considering mu, that mu is constant throughout the medium. So simply epsilon and mu are independent of the spatial quantities what we have. Then it is said to be the homogeneous. So if it is simply constant, then it is said to be the linear. If it is not depending on the direction, then it is said to be the isotropic. Just remember these points, and what we are assuming is the medium what we are considering is a homogeneous medium, and it is charge free initially. There are no charges in that one, that the charges are it's very far away from that one. So the wave will be just traveling through that particular medium, that simply it is a charge free homogeneous medium, that what we are assuming. Since charge free, definitely we can say that there will be no charge densities. Now we have to modify this equation, that del dot D is equals to rho V, which corresponds to del dot D is equals to 0. Why it is 0? There are no charges. Since it is charge free region, rho V is equals to 0. Now replace this D with epsilon E, that this can be written as del dot epsilon E is equals to 0. Del dot epsilon E is equals to 0 once again can be written as del dot E is equals to 0. Since we are considering a homogeneous medium, that epsilon is independent of this del operator. Therefore, we can take this equation simply as del dot E is equals to 0. Since epsilon is not equals to 0, obviously del dot E is equals to 0. That is the equation what we are supposed to consider for a charge free region. That consider this as equation 1. That is very much useful for us. And consider the second equation, that is del dot B is equals to 0. Magnetic monopole does not exist. That del dot B is equals to 0 corresponds to del dot, instead of B what we can write, it's a mu H, del dot mu H is equals to 0. Once again, the medium is a homogeneous medium. Since it is homogeneous medium, mu is independent of delta, you can bring it out. After that one, since it is not equals to 0, obviously del dot H is equals to 0. So what we can write is del dot H is equals to 0. This is the next equation what we are supposed to remember. After that one, let's consider the third equation for our electrostatics, that is del cross E is equals to, So what I am doing is I am considering that one in phasor domain as a phasor notation. Minus j omega b, that dou by dou t term can be replaced with j omega dou b by dou t, right? So it is dou by dou t is replaced with j omega, b can be written as it is and a negative sign is there. Now replace this b with mu h, that del cross E is equals to minus j omega mu h. This is the equation what we require to derive wave equations. So keep it aside. Go for the fourth equation, that is also will be considered in phasor domain. The fourth equation that what we have is del cross H is equals to J plus dou d by dou t. If you remember that one, we can modify that. J plus dou d by dou t. J is conduction current density. Conduction current density can be written as sigma E. Therefore, simply this can be written as del cross H is equals to J plus, so dou d by dou t. Dou by dou t can be replaced with J omega d. Right. So simply this is a phasor notation of our fourth Maxwell's equation. Del cross H is equals to sigma E plus j omega d, which is nothing but our Ampere's law. Right. Next, sigma E plus j omega d can be written as epsilon E. That is sigma E plus j omega epsilon E. So if you take that E common, then this implies del cross H is equals to sigma plus j omega epsilon multiplied with E. So this is our fourth equation. So these four equations are derived in our time varying fields. Now we are using those time varying equations by applying a special condition that it is simply charge free region. Right. Now how to modify this? So whenever we have some free space, just make this sigma is equals to 0 and replace this epsilon with epsilon naught, mu with mu naught. Like that, what we have to do is you have to vary these equations according to the conditions what we have or the medium what we have. And clearly remember, these four equations are the base equations we are supposed to take, and from those equations we will derive a pure electric field equation as a wave and a magnetic wave equation. Now just these are the four equations what we just observed now, and I compiled them, I wrote here. Now using these four equations we are supposed to derive the wave equations. For that, a simple mathematical manipulation is there, nothing more than that. Consider either equation 3 or 4. If you consider equation 3, we will get a wave equation for electric field. If we consider equation 4, we will get a wave equation for magnetic field. So what we do is just we will observe one wave equation, the similar form will be applicable to the another field also. So I will take this equation 3, that take equation 3 and apply curl on both sides. That simply remember, curl will be applied on both sides for our equation 3. That simply can be written as del cross E, that I am applying a curl on both sides. So that's the left hand side now applied. Right hand side also I will write that j omega mu can be treated as constant, simply it is del cross H. So just apply curl on both sides. Now observe, it's a vector triple product. This is similar to the vector triple product. Then you can write down the equivalent of this one on the left hand side. How we can write this? So the gradient of divergence of E minus a Laplacian of E, that is on the left hand side. So gradient of divergence of E minus del square E is the equivalent of this curl E. So which is equals to minus j omega mu. What is del cross H? Directly you can take this del cross H from our fourth equation. The del cross H can be directly replaced with sigma plus j omega epsilon E. It's a very simple one. So take this equation, substitute here and write down the equivalent of this one on the left hand side. Now from equation 1, how this del dot E can be replaced with 0. So gradient of 0 is 0. So on the left hand side clearly 0 minus del square E, which is equals to minus j omega mu sigma plus j omega epsilon E. This is the thing that what we have. Now what I do is just I'll assume this entire thing as a constant gamma square. Later we will discuss what is that gamma. So this entire thing can be written as a constant gamma square. So what is the equation now? So on both sides this negative sign will be cancelled, that del square E is equals to gamma square E. So if you write down this one as an equation, simply this is del square E minus gamma square E is equals to 0. So clearly observe here, this is a pure equation of electric field intensity. that there is no magnetic field intensity. So if you want to describe how the electric field wave is propagating, then we have to use this particular equation, that del square E minus gamma square E is equals to 0. Here remember, this E is not a simple quantity, this is a vector quantity, and the vector may be a combination of the three field components what we have in our respective coordinate system. If you are considering the rectangular coordinate system, this E may be a combination of Ex, Ey, Ez. If you are considering that one in our spherical coordinate system, r, theta, phi. Like that, what we have to do is just we have to observe it's in which coordinate system this E is described. So later we can obtain the solution for this particular equation also. But before that, so what is the equation of our magnetic field? So the magnetic field wave equation also can be in the same form. For that, what we have to do is we have to take this equation, that del cross H is equals to sigma plus j omega epsilon E, and then apply curl on both sides. Simplify using the equations that what we have. Then a similar type of equation what we obtain is like this, that is del square E minus gamma square E is equals to 0 is for E wave, and del square H minus gamma square H is equals to 0 for H wave. Combinedly, these two equations are called as Helmholtz equations. Remember, these are the basic equations, or the base equations for any wave propagation. Whatever may be the electromagnetic wave you are observing, clearly these are the basic equations. They are called as Helmholtz equations. What we have to do is just we have to interpret these equations. If you obtain the solution for this particular equation by assuming some conditions, then clearly we will get an electric field or the electric wave equation. From that, as we know, electric field and magnetic field are related, we will get magnetic field equation also. So whenever we have a medium, and if you get the solution using this solution for this particular thing, then electric field, magnetic field, each and everything can be observed, right? So these two equations are called as simply Helmholtz equations. Remember them. Here clearly we defined one quantity. It's in the simple derivation. It's meanwhile we gone through one simple quantity called as gamma square. So what is that gamma square? Just observe what is gamma square. Gamma square is equals to what we wrote or what we took is j omega mu sigma plus j omega epsilon. And from this one, how we can write this gamma? Gamma is equals to under root j omega mu multiplied with sigma plus j omega epsilon. Clearly remember, this gamma is a very important quantity which describes how the wave is propagating in a particular medium. That's why it is a combination of an attenuation factor as well as a phase constant. That attenuation factor will be denoted with a symbol alpha, and the phase constant will be denoted with a symbol beta. So always remember, this gamma is a propagation constant for this particular medium, and if you remember this equation, it will be utilized for another topic also, like a transmission lines. In the transmission lines also we have a similar type of equation, but the quantities may vary. There we will consider the transmission line parameters, here we are considering the medium parameters, nothing more than that, right? So just you remember this basic equation, that gamma is equals to j omega mu sigma plus j omega epsilon. A similar form will be there also, right? What is this one? This is a propagation constant. So it describes how the wave will be propagated using attenuation factor as well as phase constant. How much attenuation will be provided so while the wave is traveling, or how much attenuation will be attained by that particular wave while the wave is traveling in a medium can be observed using this alpha. So that simply attenuation factor describes how the attenuation is taking place, and this will be measured in Napier per meter. The units of this alpha is Napier per meter. And while the wave is traveling, how much phase shift is taking, it's with respect to the distance what we are considering, can be described using our phase constant beta. So this will be measured in radian per meter. So simply the propagation constant is a combination of these two. Now just remember these equations, don't go for any complex derivations. Just I'll give you what is the equation for alpha and what is the equation for beta after getting a square root of this particular complex quantity. Since it is complex quantity, it's directly may not be possible. So with some other mathematical procedure, we can get the equations for alpha and beta, right? The alpha and beta equations are like this. So alpha is equals to omega under root mu epsilon by 2 under root of 1 plus sigma by omega epsilon whole square minus 1. So after getting the solution for this square root of this particular complex quantity and making the real part to this alpha equals to alpha, then what we get is this one. So Napier per meter, the units are same, and here it is beta, and don't go for any other complex formula, just you put a plus sign here, then that will be equals to beta. Omega under root mu epsilon by 2 under root of 1 plus sigma by omega epsilon whole square minus 1. Here it will becomes plus 1, right? So the same equation, but here what we have is plus 1. These two are the two equations which are useful for calculation of our attenuation factor as well as phase constant when any problem is given just directly in terms of our mu epsilon sigma omega, right? Otherwise there is another simple procedure. Don't go for these equations, just remember this one. That's enough. If you remember this particular quantity, we can derive alpha beta from that one, right? Simply this particular term is nothing but our propagation constant. Clearly remember this. Propagation constant is very much useful in understanding the wave. Now we are supposed to get the equation for the solution for wave equation. So if you get solution for wave equation, clearly you can interpret. So what are different characteristics of it? For that, what we have to do is initially we have to choose a proper wave. So what is the type of wave we are choosing is a plane wave, and it is a uniform plane wave. So what is uniform plane wave? The name itself indicating uniform. Uniform means a uniformity will be there in its amplitude and phase. Where the uniformity will be? On a plane. So here clearly imagine how the property of that particular wave was characterized. So here we are considering electric field and magnetic field on a plane. All these planes will parallel while they are propagating in space, right? Now on this plane the amplitude and phase both are uniform. That's why it is called as a uniform plane wave. Now we are supposed to take a uniform plane wave and we are intended to get the equation for or the solution for that uniform plane wave. For that, what I do is I will take the electric field initially. We can take magnetic field also, no problem, but what I do is for our convenience I will take the electric field and try to define that electric field equation, and from that one try to get the solution for that. And before that, so what is a wave? So what is the parameters which are variable in that particular wave equation? Clearly identify wave is a function of both distance and time. So whenever we are representing a wave, we are supposed to take that wave equation as a function of both space and time, or distance and time. So here what we are supposed to do is, let us take the electric field intensity or the electric wave, that E can be written as a function of space, that is nothing but distance z, it's represented with some z, and t, right? Here for our mathematical convenience, what I do is I'll assume that for a uniform plane wave the electric field is in the direction of x, that the electric field is in the direction of x, and that particular electric field or the wave is traveling in z direction. Clearly remember this assumption. This is an assumption. The electric field is in the direction of x and it is traveling in z direction. So here clearly what you can understand is the variation of the x component is along z direction only. That the x field component is not varying along y direction, the x component is not varying along x direction, but it is varying along z direction. So for that, what I do is just I will define the equation of this wave like this. It's along with time factor E of z comma t into e power j omega t. Simply is a sinusoidal variation which is added to describe the time dependency of that particular wave. So E of z into e power j omega t is our wave equation, that what we are assuming initially, but here clearly remember we suppress that time factor for our mathematical convenience, nothing more than that. For the mathematical convenience, just suppress this time variation, that e power j omega t term will be neglected in further equations. And what we are assuming is that E field is in x direction, that I will add a suffix x to it. So here clearly Ex of z is the wave equation which is a function of just space, and e power j omega t was neglected. So for our mathematical convenience, what we are doing is we are suppressing this time variation, that e power j omega t is suppressed, and for our understanding just I have added a suffix x here, that the electric field is in x direction and it is propagating in z direction. So what we are supposed to do is we are supposed to get this Ex of z, that Ex of z is the main motto, that what we are supposed to get, right? Now for that, what I do is I will consider the equation that what we derived called as Helmholtz equation, that del square E minus gamma square E is equals to 0. That is the basic equation, right? Here we have to divide that entire expression, or we have to expand that entire expression, that expand this del square operator. If you expand this del square operator, simply it is dou square E by dou x square, and for our convenience once again I am considering only rectangular coordinate system, dou square E by dou x square plus dou square E by dou y square plus dou square E by dou z square minus gamma square E is equals to 0. That what we have here. Now observe here clearly, E is equals to only Ex of z. Since I suppressed this particular quantity, remember that only Ex of z is the quantity what we are supposed to take and substitute here, and that what I do is I will write Ex of z here itself for our convenience, that Ex of z everywhere, that what I add, that dou square Ex of z by dou x square plus dou square Ex of z by dou y square plus dou square Ex of z by dou z square minus gamma square E is equals to 0. But once again recollect, this Ex is a variable with respect to z only. It is independent of x, it is independent of y. So the dou by dou x, or dou square by dou x square term and dou square by dou y square term, both are equals to 0. That these two terms will be equals to 0, and the remaining term is just dou square Ex of z by dou z square minus gamma square. Here also I can write this one as Ex of z is equals to 0. That simply, that is a second order differential equation. We can obtain the solution for that second order differential equation, and we have a standard solution for that. So what is the standard solution for this particular equation? That Ex of z simply can be written as E naught plus e power, here what we have as a constant, that is e power minus gamma z plus E naught minus e power plus gamma z. Clearly remember, this is a standard solution for this particular second order differential equation. This is one of the solutions that what we have. So here clearly Ex of z is equals to E naught plus e power minus gamma z plus E naught minus e power plus gamma z we have. Now interpret those two terms. So what are those two terms? The first term will describe the wave which is propagating in positive z direction, so or in a forward direction. Simply the wave propagation in forward direction can be described with this particular term E naught plus e power minus gamma z. And the wave which is reflected will be described with this particular quantity, that is, this is a wave which is traveling in negative z direction. That if there is any reflection, we are supposed to consider this particular quantity also. The combination of the positive one and the negative one is said to be the entire wave. But here what we are considering is a boundaryless medium, that the medium has no boundary. Since it has no boundary, there will be no reflection. The wave is entirely travels to the infinite. If the wave entirely travels to the infinite, since it has no reflection, clearly the positive direction wave only we are supposed to consider. That's why what I am doing is I am neglecting this particular term. Don't consider, because we are considering a boundaryless medium, that when the wave is traveled for an infinite distance, it's obviously the amplitude of that reflected one is obviously 0. Therefore clearly we can write Ex of z as a simple quantity E naught plus e power minus gamma z. This is a simple wave equation which is depending on only distance. But what we require is a wave equation which is depending on time also, that is a function of both distance as well as time. So what I do is now I will take the time parameter to the equation. So initially I suppressed that one, now I will bring this one to here to get a pure equation of our wave. So for that, just multiply this entire one with our e power j omega t. So take this Ex of z and multiply that one with e power j omega t, then what we get is a pure wave equation. Then E of z comma t can be now expressed as E of z comma t is equals to, this is E naught plus e power j omega t, this e power j omega t brought here in between these two, multiplied with e power minus gamma z. That is E naught plus e power minus gamma z is the original equation, and multiplied with e power j omega t now. Now which is equals to simply E naught plus e power j omega t e power minus gamma z. How we can write this gamma? Gamma can be written as alpha plus j beta z. And once again clearly remember, for our mathematical convenience and a proper form of the equation we require, I am considering real part of this particular quantity. Don't consider the imaginary part. Just we consider the real part of this particular quantity. For that, once again I have to rearrange this equation, that which is equals to E naught plus e power, here j omega t is there, minus j beta z is there. So what I do is I will take this j common, then it is omega t minus beta z multiplied with e power minus alpha z. Just this is the equation that what we have. E power j omega t can be written as cos omega t minus beta z plus j sin omega t minus beta z, right? Just remember, that is a simple mathematics. Now what I do is, once again I am saying that for our mathematical convenience and for a good form or a proper form, I will consider the real part of this entire equation. So consider the real part of this equation, that is E naught plus, this can be written as, or before that just you write down this one, and this can be written as cos omega t minus beta z plus j sin omega t minus beta z. That what I expanded, E naught plus e power minus alpha z, this entire thing that I expanded. And once again for our mathematical convenience, I will consider only real part of this one. Simply what is the real part of this one? Ignore this term, and the entire one is our real part. So the equation of our electric field, which is a function of both space and time, that is nothing but E of z comma t, can be written as E naught plus e power minus alpha z cos omega t minus beta z. That is the equation that what we require. I will write here. That is clearly that the equation of our electric field E of z comma t, which is equals to, the real part of this one is E naught plus e power minus alpha z cos omega t minus beta z. Now just observe that particular equation. Clearly that is a sinusoidal variation. So the wave which is propagating, the electric wave which is propagating in medium is a sinusoidal variation. And here we have different parameters. The amplitude of that sinusoidal variation is E naught plus e power minus alpha z. So clearly the initial amplitude E naught plus, set z is equals to 0, the amplitude is E naught plus, right? The initial amplitude will be affected by this factor e power minus alpha z. So clearly this alpha can be treated as a quantity which describes the attenuation for that particular wave. That's why it is said to be the attenuation constant. While the z increases, e power minus alpha z also increases, right? So the effective amplitude of that particular wave reduced. In the same way, the phase of this particular term, that is cos omega t minus beta z, will depend upon beta. So if the beta is varying, obviously the phase is also varying, and clearly this phase is depending on time also. So clearly as the time moves, as the time increases, the phase of the signal is also varying. How, with which rate the phase is varying, that what we require. Before that, just remember simple point, as the wave is traveling from one point to another point in any medium, obviously it attains some attenuation. That attenuation will be described with this factor e power minus alpha z, and the phase of that particular wave is also varying. The phase variation can be described with this entire factor omega t minus beta z. Now what we require is with velocity, with which velocity the phase is varying. For that what we have to do is we have to take that phase term and we have to go for some other analysis, that we require with which velocity the phase is varying. Now consider the equation what we derived, E naught plus e power minus alpha z cos omega t minus beta z. This is the basic equation. As we discussed, this is the amplitude quantity and this is the phase quantity. Now at any point in the free space or the medium, not free space, in the medium, lossy dielectric medium, consider this phase, that omega t minus beta z at any point may be some constant. Just we are observing that one at a particular constant, so there is no variation in that particular phase. Therefore omega t minus beta z is equals to k at that particular point. Now obtain z from this one, that beta z is equals to omega t minus k, that what we can write, z is equals to omega t by beta minus k by beta. That the distance at that particular point is equals to omega t by beta minus k by beta. Now, if the distance is varying with respect to time, as the time moves on, the distance also varies. So, what we have to do is just we have to observe that the variation in that particular distance. For that, differentiate this one. dz by dt we want the variation in the distance with respect to time. What is dz by dt? Which is equals to, for the first term, simply it is omega by beta minus 0, which is equals to omega by beta. What is distance by time? Distance by time is nothing but velocity. That it describes some velocity. What is that velocity? Of the variation of the phase. So clearly this dz by dt is equals to omega by beta is called as phase velocity, with which velocity the phase is varying while the wave is traveling in a particular medium. So simply remember, this omega by beta is a very very important one, which describes phase velocity, that what we have. And what are the units of phase velocity? Obviously meter per second, right? Let's check whether we are satisfying this particular meter per second or not. What are the units of omega? Omega has a radian per second, that omega units are radian per second. And what are the units of beta? Beta has radians per meter, so it is radians per meter, so simply it is meter per second. So the left hand side, right hand side, so both are same. Clearly remember that phase velocity described with Vp describes, or denoted with Vp describes with which rate the phase is varying. So this is one of the important parameters we are supposed to remember. Now we are supposed to get the equation for magnetic field also. So till now we discussed about the electric field and what is the equation of that particular electric wave, but that is not only sufficient. We require the magnetic field, or Maxwell's equations can relate our electric field with magnetic field. So what I do is I will take that Maxwell's equation and I will try to get the magnetic field equation also. For that, before that, just let us write what is the equation which is right for our E. E is equals to, simply it is E naught plus e power minus gamma z. Once again, for our mathematical convenience, I suppressed here time constant, that E naught plus e power minus gamma z is E. Using this E, I have to derive our Maxwell's magnetic field. That for that, let us take the Maxwell's equation, del cross E is equals to minus j omega mu h. That I will expand this del cross E on the left hand side. If you expand this del cross E, this is ax, ay, az. Here what I am doing is I am taking the rectangular coordinate system. Ax, ay, az, and the quantities of del are dou by dou x, dou by dou y, dou by dou z. And what we assumed is this electric field is existing only in x direction, that it has only x component. That's why initially it was described as Ex of z, right? So that's why I will take this particular quantity only for x, that is E naught plus e power minus gamma z, that is only for electric field which exists in x direction. And for y direction there will be no electric field. For z direction also there will be no electric field. That Ey and Ez are made zeros, which is equals to just j omega minus j omega mu, and I am expanding this h in rectangular coordinate system. That I will consider the entire coordinates, hx ax plus hy ay plus hz az. I will consider the entire components, right? So the left hand side, so I expanded this del operator with curl operation, and on the right hand side just I wrote this as a combination of hx, hy and hz. Now come to the left hand side, and what we have here, ax multiplied with dou by dou y of 0, 0 minus dou by dou z of 0, 0. And the second term minus ay of, that what we have is this term, so dou by dou x of 0 minus dou by dou y of this particular quantity, that what we have, that dou by dou x of 0 minus dou by dou z of, this is the quantity that what we have, dou by dou z of E naught plus e power minus gamma z, that what we have here. So once again, ax this is 0 minus 0 minus ay 0 minus dou by dou z of E naught plus e power minus gamma z, that's right, plus az multiplied with the third term dou by dou x of 0, 0 minus dou by dou y of this particular quantity. Since this quantity is not a function of y, that is also equals to 0. That dou by dou y of that particular quantity is 0, which is equals to, on the right hand side, the entire term remains unaltered. There will be no change in that one, which is equals to minus j omega mu hx ax plus hy ay plus hz az. Now clearly observe here, on the left hand side, ax multiplied with 0, az also multiplied with 0. That means there is no x term and y term in the right hand side also, if you compare that unit vector formula, unit vectors. So simply this ax is 0, az is 0, corresponds to hx quantity is 0, hz quantity is also equals to 0. So only hy quantity remains for us. So just you write down what is that hy quantity which is on the right hand side initially. That is j omega mu multiplied with hy ay. That is the quantity which left for us on the right hand side, which is equals to, on the left hand side, that what we have, minus of minus plus, it is dou by dou z of E naught plus e power minus gamma z. This is the term which is left side remains for us along with its unit vector ay. So if you compare them, just hy j omega mu is equals to dou by dou z of E naught plus e power minus gamma z. That is the quantity what left for us. So before going to simplification of that one, just imagine so what's happening here, or observe what's happening here. We are assuming that the electric field is existing in x direction. That is the initial assumption what we took, and we derived the equation, we solved that one, and using our Maxwell's equation we got h, but the h will consist of only one component, that is in y direction. So clearly the electric field is in x direction, the magnetic field what we have is in y direction, and the wave is propagating in z direction. This is the assumption, or this is the observation that what we have. Now go for the simplification. So here clearly this is the equation that what we have. Now take this equation, minus j omega mu hy, I ignore this unit vector on both sides, dou by dou z of this one, that E naught plus is constant and e power minus gamma z as it is, and the internal derivation of this one is minus gamma. That here clearly minus j omega mu hy is equals to E naught plus e power minus gamma z into gamma. Once again, what is this E naught plus e power minus gamma z? E naught plus e power minus gamma z itself is Ex, right? So simply this entire term can be replaced with Ex, and both sides we have a negative sign, just neglect them. Then what we have is j omega mu hy is equals to Ex multiplied with gamma. Then we have a very simple relation between this Ex and Ey. That's a very simple relation, nothing more than that, Ex and Hy. J omega mu Hy is equals to Ex into gamma. What we do is we will try to confine that particular equation, and we will try to get some other one like this, that I will take the ratio of Ex to Hy. Remember this Ex is nothing but Ex of z, Hy is nothing but Hy of z. So Ex by Hy is equals to j omega mu by gamma. Already we have some quantity gamma. What is gamma? Just take gamma here and substitute. Then this can be written as j omega mu divided by under root j omega mu multiplied with sigma plus j omega epsilon, that what we have earlier. So if you simplify that particular quantity, then what we get, Ex by Hy is equals to, the numerator now becomes square root of j omega mu divided by sigma plus j omega epsilon. So just observe, we have some complex quantity here. That complex quantity is a division of Ex with Hy. What is Ex by Hy? How to interpret this particular quantity? That what we are supposed to do is, we are supposed to get some equation for magnetic field. That we got the magnetic field equation, that the magnetic field equation Hy is equals to Ex into gamma divided by j omega mu. But if you take the ratio of this Ex to Hy, we are getting some other complex quantity. How to interpret this complex quantity, and what is the unit of that particular quantity? For that, come to the left hand side. What are the units of our Ex? Volt per meter. What are the units of Hy? Ampere per meter. Volt per meter divided by ampere per meter is simply nothing but volt per ampere. What is volt per ampere? Impedance. So the quantity what we have for this particular thing is nothing but impedance. That's described as characteristic impedance of the medium. That whenever we have some medium, that the medium will have some characteristic impedance. That's characteristic impedance purely described with the medium properties like epsilon, mu and sigma. How to interpret that? There is no physical form of that particular impedance, but we need to say that that entire medium has some characteristic impedance, and which is equals to under root of j omega mu by sigma plus j omega epsilon, and it is denoted with a symbol eta. Now clearly we have a pure relation between our E and H, that E by H is always equals to the characteristic impedance of the medium. That's why clearly remember Ex of Z divided by Hy of Z is equals to eta. That eta is nothing but under root of j omega mu by sigma plus j omega epsilon. Same as our gamma. If you remember this eta, this will be useful for remembering another equation in transmission lines. It's a very easy one and very simple one, right? Now how to get the equation for this Hy of Z? You may think that the equation for Ex of Z and Hy of Z are same in form, that where what we have is E naught plus e power minus alpha Z cos omega t minus beta Z, right? Here what we have to do is we have to add some other phase variation for magnetic field also for mathematical convenience. So what I do is I'll try to write down the equation of Hy. So how to write down the equation of Hy? Ex of Z divided by eta. So here clearly the equation of H can be written as Hy of Z is equals to Ex of Z divided by eta. What is the equation of Ex of Z? If it is time varying, then simply we have to consider time factor also here. That's why what I do is I'll take this one as Hy of Z comma t, a time variation of the magnetic field also I am considering, that the suppressor time varying now I am adding here, that this is simply Ex of Z comma t by eta, which is equals to, what is the equation for Ex of Z? It is E naught plus e power minus alpha Z divided by eta. This entire factor is now our amplitude factor multiplied with the time variation cos omega t minus beta Z remains as it is, but along with some phase shift, that what I do is I'll add some other phase shift minus phi. Clearly remember for the magnetic field why we added that phase is for only mathematical convenience, and if there is any phase shift because of this eta, that phase shift will be added here. If there is no phase shift, a pure form will be remains as it is, but the eta has some other phase shift, that phase shift will be added here to observe and understand it clearly. So we got two equations, that's for electric field intensity in the x direction. Ex of Z is equals to, so what is the equation for that one? E naught plus e power minus alpha Z cos omega t minus beta Z. That is only the equation for Ex of Z. Next, the modified equation for Hy of Z comma t is equals to E naught plus e power minus alpha Z by eta cos omega t minus beta Z minus phi. That phi was extra added to that particular equation to get, that's a very good form. These two are the two equations what we require, and how they are related. So Ex by Hy is equals to eta. So if x and y components are given, directly you can calculate eta. But some special case Ey and Hx are given. How to obtain that eta? Very simple. Remember Ey of Z divided by Hx of Z is also equals to eta, but with a negative sign. That what we are supposed to do is Ey of Z divided by Hx of Z is equals to eta, but put a negative sign before that. No, Z components are given to us. So Hz is given, Ex is given, then the ratio is same. That what is given to us? Ex of some y is given to us, and Hz of y is given to us, then this is also equals to eta, no doubt about it. But here we have to add a negative sign. Then you may get doubt, so when I have to add negative sign, when I have to take this positive sign, simply follow the cyclic rule, x to y positive, y to z positive, z to x positive, x to y positive, y to x negative. If it is x to if it is z to x positive, but it is here x to z, that's why it is negative. So clearly remember for this eta always x, y, z. Thus the simple right handed coordinate system rule is applicable. Ex by hy plus eta, ey by hz plus eta, ey by hx minus eta. Just remember a blind formula, right? So this is a simple relation between all these things that till now we derived the electric field intensity equation. So meanwhile the electric wave equation, meanwhile we gone through one of the constants called as propagation constant. That propagation constant is a combination of alpha and beta. We gone through the equations of that one. Later we derived our magnetic field equation or the magnetic wave equation. Meanwhile we got another quantity called as eta, that is nothing but our characteristic impedance of the medium. So this is a very simple one. So later we are going to define another simple quantity called as loss tangent. How to define that loss tangent? So very simple. Take our equation that del square E minus gamma square E is equals to 0. The del square E minus gamma square E is equals to 0. That's how this gamma square was described. The del square E is equals to, instead of gamma square I can write j omega mu sigma plus j omega epsilon E. That entire gamma square is written like this. Clearly observe here we are adding sigma to this complex quantity. That sigma plus j omega epsilon was taken as a single term. So another term was defined for this particular combination, that is sigma plus j omega epsilon, called as a complex permittivity and represented with j omega epsilon c. It is represented as complex permittivity. The complex permittivity can be taken as sigma plus j omega epsilon. Now what is this complex permittivity epsilon c, which is equals to sigma by j omega plus epsilon. This can be written as epsilon minus j sigma by omega. That's what we have. Now here we have to define the loss tangent. The loss tangent was defined as simply the ratio of magnitudes of imaginary quantity to the real quantity of that complex permittivity. So what is the magnitude of imaginary quantity? Sigma by omega. And what is the magnitude of real quantity? Epsilon. So the loss tangent was defined and denoted with the symbol tan theta loss, which is equals to the magnitude of imaginary quantity sigma by omega divided by the magnitude of real quantity epsilon, which is equals to simply sigma by omega epsilon. So here what we do is we will describe this particular quantity, or we will take this particular quantity to describe the characteristics of a medium also. Sometimes what we do is we will examine this particular quantity. If it is very very high, the loss is high. If it is very very less, the loss is less. If it is zero, simply it is lossless. So purely depend upon this particular quantity also we can describe the characteristics of a medium. That's why sometimes what we do is we will take the loss tangent, which is equals to sigma by omega epsilon, for describing the characteristics of medium. And another way, this loss tangent was defined as the ratio of our conduction current density to the displacement current density. So what is the conduction current density? Amplitude. The conduction current density is simply Jc divided by displacement current density Jd. What is conduction current density? Sigma E. And what is the magnitude of displacement current density in its phasor form? The magnitude of displacement current density is j omega epsilon E. So simply it is j omega epsilon E, the dou d by dou t. So Jc is equals to sigma E, Jd is equals to j omega epsilon E, which is nothing but simply sigma by omega epsilon. So we can take any of these two, that is from the complex permittivity we can take this loss tangent, or from the ratio of conduction current density to the displacement current density we can take the loss tangent. Whatever it may be, the equation is same, that is sigma by omega epsilon. That sigma by omega epsilon is very important for describing the medium. If it is very very high, once again recollect that sigma by omega epsilon is very much greater than 1, then it is said to be a lossy medium, or sometimes it is simply conductor. And this sigma by omega epsilon is very much less than 1, then it is said to be lossless, and this is equals to 0, that sigma by omega epsilon is equals to 0, simply it is a purely a lossless. It is low loss and it is lossless. Now what we have to do is we have to observe this particular quantity for different mediums, right? So till now we gone through few parameters like the field equations and characteristic impedance, propagation constant, loss tangent, like that. What we have to do is we have to compile those equations. After compilation, we have to modify those quantities for different types of mediums. So remember, all these are derived for a lossy dielectric medium, that is a general medium. Since it is a lossy dielectric medium, so these equations can be treated as a general equations. These general equations will be modified for a lossless dielectric medium. These equations will be modified for free space, they are for conductor. Like that we will observe all those cases.